Hello and welcome. Introduction. So this video is a continuation of my video series on the task scheduler. Now in part one, we looked at how to schedule one task. Now in this particular video, I would like to discuss how to schedule 3 tasks. Scheduling 3 tasks. Now, the ATmega 328P has 3 timers, and these timers can be used to control the execution of 3 different tasks. Now, I have discussed these timers in my previous videos. You can refer them. I'll put the link in the description. The first video that you might be interested is in video 60, generate time delay using the ATmega 328 timer 1 in normal mode. And the second video is video 74, programming the ATmega 328 timer 0 and timer 1 in C. All right, so you might want to refer to these videos for more details. Now, coming back to this video, now I mentioned that we are going to use these 3 timers to control the execution of 3 different tasks. Now, this can be achieved by using separate interrupt service routine or ISR to control or to perform each task. Now, in the next frame, or in the next slide, is a framework of an application using 3 independent timers to perform the 3 tasks. Okay, so here is the framework. Now, this framework uses 3 independent timers to execute 3 tasks, as mentioned earlier. Now, before I go any further, let me just clarify something. This framework, I've taken it out or adopted it from a book called Patterns for Time-Triggered Embedded System by Michael J. Pond. So I've taken this framework from this book. Now you can download this book for free legally because Michael J. Pond is actually giving it out for free. So I'll put the link for this download in the description. Now let's get back to this framework. Now this framework is actually a very comprehensive guide on the development of something called time-triggered patterns for embedded system. Now, if you want to know more about time-triggered embedded system, please get this book. It's a great book. I highly recommend it. All right, so let's take a look at this framework. So here we have the include directives. By the way, this is not the code itself, right? This is just only the framework. Here I define the LEDs attached to the various bits of port D of the AVR microcontroller. And then here I declare the functions that is going to be used. And here are the some of the details of the main function. Now there are very little details in the framework. The details will be coming up soon. And here I defined the functions again, as mentioned earlier. All the details are omitted for the time being. So I have, remember, in the they have 3 functions, so you need to declare or define the functions here. So init timer 0, init timer 1, and init timer 2. And here I define the interrupt service routine. Now these interrupt service routines will serve as the task. All right, because there are 3 timers, so there will be 3 independent interrupt service routines. So the first one is this ISR bracket timer 0 underscore OVF underscore VECT. Again, not much details here. It's just a framework. It's very abstract. Then the second task or second ISR is this timer 1 underscore OVF underscore VECT. And then the third ISR is this timer 2 OVF underscore OVF underscore VECT. So we'll go into the details of this in a few moments. Okay, at this point, what I'd like to do is to do a quick recap of how to calculate the values used by the timers. All right, so now for timer 0 and timer 2, the maximum delay that these timers can generate is 16 milliseconds. Now the details of this can be found in my previous videos. Now, as you can see, as you might know, that 16 milliseconds is a very short duration. Now, how do you get the timers to generate a longer delay? Let's say a 1 second delay. How do you get it to generate a longer delay? Now, the solution is to create or set up a variable to check the number of times the timer complete the 16 milliseconds. So the details of how this is done will be coming up soon. And I have discussed this in video 74, programming the Atmega 328 timer 0 and timer 1 in C. And then please refer to the link in the description. So let's get back to this timer 0. Now, for timer 0 to generate, let's say, a delay of 0.5 seconds. So what I need to, as I mentioned earlier, I'll set up a variable called timer overflow count. Now, you don't have to use this name. You can use any other name for the variable. And then I get 0.5 seconds divided by 16 milliseconds. That will give me about 31.25, which I rounded up to 31. So I need to get timer 0 to complete 16 milliseconds 31 times. Now for timer 2, let's say I want to generate a 1 second delay with timer 2. Again, I can use the same variable name for it. I have 1 second divided by 60 milliseconds. That gives me about 62.5, which if I round it up, that is about 63 times. What that means is I need to get timer 2 to complete 60 milliseconds 63 times. Now you see what it means when I come to the code. Now for timer 1, the story would be slightly different because timer 1 is a 16-bit timer, whereas timer 0 and timer 2, they are 8 bits timer. So here because the Atmega 328 is using 16 megahertz on the Arduino now, so the clock frequency used is 16 megahertz. And let's say I use a scalar prescale factor of 1024. I use this particular formula, and let's say I want to generate a 2-second delay. All right, so I have a prescale factor which is 1024 divided by 16 megahertz, and that will give me 0.0065. If I take 2 and divide it by 0.00065, that would give me 30765 ticks. All right, and then if I have 65536, that's from 16 bits. All right, then that would be subtracting that. So 65536 subtract 30769, that gives me 34767, and that is equivalent to, that would be equals to a hexa of 87 CF. So this would be the value that I need for timer 1. Now you can refer to the details of timer 1 in normal mode in video 60. Again, the link for this video is in the description. The code. Now here are the include and define directives. Here, what I've done here is I've assigned a red LED label to port D, bit 2, PD2, and then the green LED label to port D, bit 3, and the yellow LED port D, bit 4. And here I declare the 3 functions that I have in the code. And here are these 2 variables, timer 0 overflow count and timer 2 overflow count, and I've declared them as an unsigned 8-bit integer. All right, so, and here is the main part of the function. So DDRD, the data direction register D, assigned it a FF hexa that will set port D as output. And here are the 2 variable, timer 0 overflow count and timer 2 overflow count. I both set them to 0 initial values. And here I declare the 3 functions that I have. Then we enable the interrupts. And here I send the main function into a loop, forever loop. And here are the details of the function, the definition. So they are almost identical. Let me just go through this timer, the initialization of timer 0, timer counter 0, set it to 0, 0, timer counter control register A, timer control register 0A, set it to 0, 0, that would set it to a normal mode, and timer counter control 0B, and set these 2 bits to 1, because I want a prescaler of 1024. Here the timer interrupt mask Z for bit, timer 0, we set it to this bit here, set it to a 1. That will enable timer 0 overflow interrupt. Now if you compare this with timer 2, basically if you notice it's almost identical except for timer counter control register 2B. There are 3 bits that you have to set to select a prescaler of 1024. So you have to take note of this. Now timer 1, as mentioned earlier, is a 16-bit timer. So I assign the initial value to timer control counter 1, 87CF. That will give me a approximately 2 second of duration. So basically, these are the details of the 3 functions. Here are the ISR, or the task. Let's take a look at this first one here. So this is for timer 0 underscore OVF underscore VECT. All right, so right here we have the timer control register 0. We set it to reset the timer to 0 here, and then we have the timer the timer counter interrupt flag 0. We set it to 1. That is to clear the overflow flag. And here, this part here, this is the part that actually what we call check the number, check the timer overflow 31 times. Why 31? Because this 31 is shown up in our earlier calculation because we want a 1 second delay for this task. So if the overflow has reached 31 times, or the timer has complete 16 milliseconds 31 times, then we flip the we invert the LED. So if the LED is a 1, it will turn to 0. If it's a 0, it will turn to 1, and then we reset the counter to 0 on the next interrupt. If this is not true, that means you haven't reached this part, then we increment the variable by 1. All right, so this is the part that I mentioned earlier, that check the number of times the timer overflows. And here is timer 1 underscore OVF underscore VECT. Now this is for timer 1. Remember, timer 1 is a 16-bit timer, so it doesn't need this statements here to check the number of times the timer overflows. So we don't need that. All we need to do is to make sure we put in the correct value. For, let's say, in our case here is 2 seconds delay. Again, this calculation was done in the early part of the video, and here is to clear the overflow flag as before here. And here this will invert a LED. So if it's a 1, we will turn to a 0. If it's a 0, we turn it to a 1. And then finally we have timer 2 OVF timer 2 underscore OVF underscore VECT. If you notice, this is exactly it's identical to the timer 0 ISR. The only difference is here we are inverting the yellow LED, right? That's the only difference. Hardware. Now, to test the code, we require some hardware. Now, here is the schematic or circuit diagram that is required for this video. Now, these 3 LEDs, they are identical. In circuit wise, they are identical. So I'm just let's take a quick look at this one here, the yellow LED. So the anode of the LED is connected to pin 4 for the yellow LED, and the cathode is connected to one end of the 220 ohm resistor, and the other end of the 220 ohm resistor is connected to ground. And this is identical for the green LED, the red LED, except that if you notice that the green LED is connected to pin 3 of the Arduino Uno, and the red LED is connected to pin 2 of the Arduino Uno board. And on this side is the wiring diagram for this schematic here. Now you may wish to pause the video, to examine this setup. Code demonstration. Okay, so this is my hardware setup. So this is the this is my Arduino Uno, and here are the 3 LEDs, the yellow, green, and red LED. Let me just now bring up the code. Here it is. So I've uploaded the code here on the ML Studio 7. Let me just very quickly go through this because we already done this earlier. So here are the definition, the define and include directives. All right, here is PD2, PD3, PD4, each given a label, red LED, green LED, yellow LED respectively. And here are the 3 functions declared and the 2 variables, the timer 0 overflow count and timer 2 overflow count. And here is the main function, this part here is to set up set port D as the output, initialize the two variables to 0, declare the functions here, enable the interrupt, and then send it into a endless loop. And here are the details of the what do you call functions. Been through this. So this is for timer, initialize timer 0. This is to initialize timer 1. And then this is to initialize timer 2. All right, and here are the interrupt service routine or the task. So this is task 0 or timer 0. And then this is for timer 1, an ISR for timer 1 or task 1. And here is the ISR for timer 2 or task 2. All right. So let me just see. So we bring these two together. What I want to show is that we now would build the project. And we have no issues. Everything is successful. And here I'm going to upload the code to the Arduino Uno. Before we do that, just give me a minute. I need to connect it to the PC. Alright, so the Arduino Uno is now connected to the PC. So now I'm going to upload the code from the Atmel Studio to the Arduino Uno. So you can see these LED blinkings, and then now you can see the red, green, and yellow LED blinking at the rate that it was designed. So green LED is every 2 seconds. I think the yellow LED is every 1 second, and then the red LED is 0.5 seconds. All right, so I'll let it run just for a little longer. All right, so that's it for this particular demo. Okay, so that's it for this video. I hope you found it useful. Now, in the next video, I will explore a scheduler written in C. So why not join me in the next video? See you then. Bye.